Welcome back to Advanced Mathematics. In this video, I want to continue what I had left over last time. We continued with mathematical induction. So in the previous video, I talked about the first principle of mathematical induction. I also talked about the well-ordering principle, and I say the first the WOB, the well-ordering principle, the first principle of mathematical induction, and the second mathematical induction. That's I'm talking about today is it mutually equivalent to each other, logically equivalent to each other. It means that from each principle, I might get the logic to prove the other principle. And in this video, I also talk about the difference between the first principle, which is the weak principle, and the strong principle, which is the second principle of mathematical induction. I will let you know the difference. I will use I also use the first principle to prove the second principle of mathematical induction. Then what is the second principle of mathematical induction? Let's go through that first, okay? Second principle of mathematical induction, or sometimes we call it a strong induction. We will see why we call it strong induction, and the other one we call it a weak induction. Okay. Then this principle goes like this: let m be an integer and let pm plus 1, pm plus 2, and so on be statement for n greater than or equal to m, we have if we have two conditions. The first condition is Pm is true. Okay, and the second condition is for k greater than n, Pm plus 1, Pm plus 2 to Pk is true, imply Pk plus 1 is also true. Okay. Then Pm is true for every n greater than n. Okay. Okay, let's look at the hypothesis of this principle. In the first principle of mathematical induction, we just assume that Pm is true, okay, and Pk is true, imply Pk plus 1 is true, okay. But for this strong mathematical induction, we assume everything from Pm to Pk is true. So that is the difference. That is the difference. That's what we call the strong induction. We assume more statement true to be true. Okay. We not only assume Pk is true. Okay. We assume Pm is true. Pm plus 1 is true. Pm plus 2 until you get Pk. All of those statements are true. That imply Pk plus 1 is true. Then we know the Pm is true for n greater than n. greater than or equal to n. Okay, so that's the difference. And why we need to learn the second principle of mathematical induction? Because in some proof problem, it's easier to use the second principle of mathematical induction instead of using the first one. Okay, some problem you use the first one, but some proven problem, you must use the second one in order to prove. Okay, so I'm going to prove this second principle of mathematical induction using the first principle of mathematical induction, so that you can see the logic, the logical equivalent between two induction. Okay, proof. So how I'm going to prove that? Okay. So in order to prove this, we know that in the first principle of mathematical induction, we assume that PM is true, right? And we assume that PK, that's imply PK plus 1 is true. So I'm going to use those hypotheses. Use those hypotheses to prove this one. So this is what I'm going to do. Again, for each n greater than n, let's call Tm this statement Pm plus 1, Pm plus 2, and Pn is 2. Okay, are true. So let me call Tm is a statement, and that statement is this: Pm to Pn, Pm to Pn is true. Okay, and we know what? We know that Pm is true. Since Pm is true, so it means what? It means that, oh, I'm sorry, this is Tn. Okay, Tn is a statement of from Pm to Pn. Okay, since Pm is true, it means that Tn is true. Okay, because Tm is a statement, Pm is true. Okay, Tn is the statement from Pm to Pn is true, and because Pm is true, so Tm is true. Okay, if now let's set up the hypothesis. If for k, if for k is greater than or equal to m, Tk is true. Okay, Tk is a statement from Pm to Pk, which is the statement Pm to Pk are true. Okay, if Tk is true, if Tk is true, if Tk is true, then by using this, all right, by using this, okay, by using this condition here, if Tk is true, then it's imply Tk plus 1, right? Tk plus 1 is also true. Okay. Tk plus 1 also true. It means the statement Pm to Pk plus 1 are true. Okay. Tk plus 1 is true. So by using, see that? You see the first induction right now. By using first principle of mathematical induction. So look at that. The mathematical instruction is say what? If PM is true, right? If PM is true, right? And PK, and if PK is true, imply PK plus 1 is true. Okay? Then Pn is true for n greater than n, right? Okay. For k for n for k greater than n. Okay. So in this case, what was that? We have Tm is 2 already, right? We have Tm is 2. And we know what we have. We know that Tk is 2 imply Tk plus 1 is 2. Then by using the mathematical induction, we can say that we can say what? We can say that Tn is true, right? It's true for n greater than n, right? For n greater than n. And if Tn is true for n greater than, it means that what? It means that Tn is what? Tn is this statement. So it means what? It means that Pn is true. Okay. For n greater than. There you go. Okay. All right. Hopefully everybody get it here. So let me go through the proof one more time. Okay, I'm using the first principle of mathematical induction to prove, and the first principle of mathematical induction we already learned last time, which is this one. Let me show you this one right here. Right, this is the first mathematical induction. Okay, okay. See, if Fn is true, and if Sk improves for k greater than m, then S is for n greater than m is true. Okay, I'm gonna put over here for n greater than m. Okay, so in order to use the first principle, I'm gonna call Tn is statement, because this is what we need to show. Right? We need to show that Pn is true for n greater than equal to m. It means that Pm is true, Pm plus 1 is true, Pm plus 1 is true, until you get Pn is true. So I call Tn is the whole statement over here is true. Okay, so if Tn is true, and because Pm is true according to what we already know here, Pm is true, right? It means that Tm is true, right? Because Pm is true. You see, this is Tn. Tn is the whole thing. Okay, if we have only Pm is true, it means that Tm is true, right? It means Tm is true. Then for m, if T, now we're gonna assume the hypothesis, right? We're gonna start with the hypothesis right now. If Tk is true, if Tk is what? Tk is statement from Pm to Pk, right? Okay. And according to condition, if Tk is true, okay, according to the mathematical induction, right? If Tk is true, Tk plus 1 is also true, right? The first mathematical induction. If Tk is true, is implied Tk plus 1 is also true. And Tk plus 1 is what? From Pm to Pk plus 1 are true, right? Okay. Then we can conclude that Tn is also true for n greater than equal to n. Okay. And greater than equal to n. And Tn is what? Tn is everything here from Pm to Pn. It means Pn is true for all n greater than equal to n. Okay. So that is how you prove the second induction by using the first induction. Okay. On the second part of this video, I want to talk about oh yes, and I already say that the second principle of mathematical induction sometimes is more useful than the first one, because you can use to prove the proven problem that cannot be used with the first mathematical induction. Okay, so on the second part of this video, I want to talk about how to use a second principle of mathematical induction to prove to prove the WOP, to prove the well-ordering principle. I'm using the second principle to prove WOP. Doesn't mean that the first one does not work for WOP, okay? But I just want to show you that using the second principle of mathematical induction sometimes it's easier, sometimes it's more helpful than to prove than the first one. Okay, so the second part, okay, I want to prove the well-ordering principle using using the second mathematical induction. And in this, the WOP, the well-ordering principle I'm talking about in this video is a set. I consider the set, and that set is the non-negative integer. It means that I'm not just talking about the set from 1 to infinity, but I'm talking about from 0 to infinity. Okay, so non-negative integer. Okay, so well-ordering principle. Every non-empty set, okay, every non-empty set of non-negative integer. Non-negative integer, I mean the set from 0, 1, 2, so on, okay, has the smallest set. Okay, so last time we talked about the WOP with the set from 1 to infinity only. So in this video, I'm talking about the set from 0 to infinity. And I will relate the proof of WOP to the second mathematical induction. Okay, and I also use the method of the proven method of contradiction to prove the WOP over here. Okay, so let's see how we're gonna do that. Okay, so in order to start with proven by contradiction, I must have the proposition, right? And at the end, I will have the invalidity that lead to the contradiction of what we propose at the beginning. Okay. Okay. So now I want to prove what? I want to prove that all the subset of this set has the smallest set. Oh, has the smallest element. I'm sorry. Okay. Has smaller element. Okay. So I will claim that I will say that if the principle is false, okay, because we prove by contradiction, right? So we must have the proposition, okay. So if the principle is false, in other words, it means that every non-empty set of this set, okay, every non-empty subset of this set, okay, I'm called the X, okay, from subset X of this set 0 to 1, 2 has no smaller element. Okay. So this is our proposition. Okay. Okay. So we're gonna use this to lead us to the invalidity to the contradiction. Okay. Of this. So if X is a subset of this and that has no smallest element, Okay, there's no smaller element. Then what happened? There's no smaller element. Just think about it. If you have a set and there's no smaller element, there's no elements in it. It means what? It means that that set is empty. I mean the set must be empty. Okay. It means that there's no number belong to that set. There's no number which is the element of set X. That's what it means, right? So we claim that let me see. Okay, before I claim, I just say that there's no, because if this set has, if any subset here of this set has no smaller element, it means that there's no number in that set. So let me say that if P sub n is a statement, okay, a statement. What statement? The statement that n this is not an element of X. This is the statement. Okay. And I want to claim that for all n is not an element of X. I want to claim that. And I want to show you that because if n is an element of X, if n is an element of X, then X has, according to WOP, right? According to WOP, it means that if n is an element, it means that it has a smaller number, right? It has smaller number. But we are over here. We just claim that, we just assume over here. We just report that this actually has this no smaller element. Okay. So you see, if this statement over here, okay, is true. Okay, if this one is true, then X must be empty, and it contradicts to our assumption. Okay, so let Pn is the statement, and does not belong, and I claim that n is not belong to it. For all n is not belong to it, and this statement I also claim that Pn is true. Okay, for all n. Okay. Okay. If Pn is true, it means n does not belong to any X. Okay. Because if n belong to a subset X, it means that according to WOP, right, n must have the small element. Okay. So it contradicts to, you see that it contradicts to what we have here. Okay. So we have to show that we need to prove that this statement here is true all the time. It means there's no n element in the subset X. Okay. So I'm gonna show that Pn is true all the time. I'm gonna show that Pn is true all the time. I'm only using the second principle. Okay. Using the second principle of mathematical induction. Okay, I'm going to show that Pn is true all the time for all n, for all n is greater than or equal to 0. Okay, I'm going to put over here. Okay. All right, so I'm going to do that. Of course, we're going to start with because right now for all n greater than or equal to 0, so over here our m is 0, right? So we start with this. Okay, our m over here is 0. So let's start with the base case first, right? We know P0 is true. Of course, P0. We know P0 is true, of course, right? Because if P0 because okay, p0 actually means 0 does not belong it does not belong to x, right? Because if it belong to x, if 0 belong to x, right? If 0 belong to x, then it means that w of p according to w the set x, then set x has small s. You see that it contradicts, right? Okay. Oh, I'm sorry. If p0 is because if p0 is it means 0. Okay, because if 0 belong to x, if 0 belong to it, then x has a smaller n. Okay. Now let's start with the second condition. Okay. For k greater than or equal to 0. Okay. We assume that p0, p1, pk is true. Okay, p0 from p0 to p1 to pk is true. Okay, and because this is imply what? This is imply this. Okay, p0, p1 to pk is true. That's easy for you to see, because if it is not true, it means that 0, 1, 2, 3, 4, 1, 2, 3, 4, 5 until k it belongs to x, right? And if it belongs to x, then what? Then x has the smallest number. Then it contradicts to what we have over here. Over here we assume that this is no smaller number. Okay, so we see that p1 and p2 and pk is true. Okay. Or in other words, we say that 0, 1, 2, 2k does not belong to x. Right? Okay, does not belong to x. And if 0, 1, 2k does not belong to x, by using the second method, it means what? It means k plus 1 also does not belong to x. Okay. And if k plus 1 does not belong to x, it means what? It means that It means that pk plus 1 is true, right? Okay, right? Because if k plus 1 does not belong to x, then it means pk plus 1 is true. Okay, and what we have here, we have pk is true, imply pk plus 1 is true. Okay, then by using the second principle of mathematical induction, we can conclude that Pn is true. Okay, in other words, n does not belong to x for set x for all n's greater than or equal to 0. Okay. And if n does not belong to x, is what? If n does not belong to x, then what we have? Okay. So if for all n does not belong to x, it means what? It means the set x. It means x is empty, right? And if x is empty, it's contradiction. Okay, if x is empty, it's contradiction because we assume that x is non-empty. Okay, So we X is analytical. X is a subset of this, so it's not. It's a contradict to this, to the proposition we propose over here. Okay, so we done the proof. All right. Okay. So I think that's all for the second video today. Next time I will be talking about another theorem, one of the most important theorem uh, in, uh, in mathematics. It's considered again. This theorem is also considered as the foundation of mathematics. But, because we don't have a time, so I'm gonna just stop over here, and I'll see you next time. Bye bye.